computation, but it's mostly a group on quantum information theory. Let me see that. I'll minimize this. I don't know why. Anyway, so then I thought that maybe I could present something that is quite fundamental in quantum physics, which is whether quantum physics is random or not, and how it compares with classical physics. This is a problem of interesting foundation, but it's also a problem that has practical applications, because randomness, as I will discuss during my talk, it's also a resource that we use for information processing, for instance, for cryptography. So let me start by saying something that stating something that is a bit of a contradiction. Even so, sometimes in many papers you find a sentence saying that quantum physics contains an intrinsic form of randomness with no classical analog. I would say that the majority of physicists or quantum physicists agree with this sentence. However, if you interact with people working in standards, okay, I don't talk to them on a regular basis, but I have some interaction with them, and they will tell you that they don't see the need of creating a new standard to certify quantum random number generations. For them, there is no need for a new standard. For them, it's just another physical random number generator. Okay, so I would say, based on my partial knowledge, so I'm not sure, I'm not totally sure about what I write here, but I would say that most of the people working for these standard authorities would agree with this sentence. And in fact, at the moment, we don't have any specific standard for quantum random number generators. Okay, so, well, probably there is I would say that there is a contradiction here, because we physicists say that it is something new. And on the other hand, people perhaps more related to computer science, they don't see the need of adding anything new to what is there at the moment and what was there without any reference to quantum physics. So one of the scopes of my talk is to resolve this contradiction, and also somehow to clarify several things about randomness and randomness in quantum physics. So I then take here some folklore about randomness, and this is a sentence that I took from a paper I wrote some time ago. And somehow one of the points I want to tell you is that I wouldn't write this sentence anymore. Okay, so what it says here is that randomness is a fundamental property of nature. I agree with this. It's also an application for cryptography, and it's also a resource for applications. I also agree with this. But then it is said that the applications go from cryptography to gambling to numerical simulations of physical systems. So we sometimes use randomness to generate passwords in cryptography, or to have online games. But we also use randomness, for instance, for Monte Carlo simulations. Okay, and this is what we wrote here. Now, perhaps one of the main points of my talk is that although we use the term randomness to describe these different applications, it's my strong belief that we are referring to, we may say, two different sides of randomness, but I would even say two different phenomena. Okay, so in the first case, for numerical simulations, we require statistical randomness. So we need a sequence of bits that has no pattern. Okay, so this is what I'm going to call statistical randomness. And here it's irrelevant if someone can predict this statistical this series of bits. Okay, so the only thing we want is that there is no pattern. So this means that, for instance, if we have a list of n bits, we want that the entropy of the n bits is equal to n bits. Okay, so this is the only possibility for this to happen, is that each bit is like a perfect coin that we flip. Okay, this is the only possibility of having n bits of entropy in n bits. And the way people test this is by usually checking some statistical test. For instance, those prepared by NIST, the National Institute for Standards and Technologies. And these tests look for patterns in sequences. And if you don't pass this test, then there are patterns in your sequences, and these sequences are not good for numerical simulations. However, when you talk about cryptography, you require something that I will call in my talk private randomness. So here, I mean, lack of patterns is important, but what is really important is that no one can predict your result. So there might be patterns as well, but what you really want is that the predictability is not complete. Okay, you want to use it. You don't want that someone can predict your password, right? This will become clear later what I mean. And also what I want to say is that NIST test, the statistical test, don't measure this property, okay? Because this is not a property that you see in sequences, it's a property about physical devices. And these things will become clearer. And then the figure of merit, what you want to optimize is not the entropy, but it's the entropy that an eavesdropper, an enemy, Eve, usually called Eve or E or eavesdropper, sees. Okay, so this is why instead of having the entropy of my sequence of bits, I have the entropy of the sequence of bits conditioned on what an enemy can know about my system. And what we know is that this conditional entropy, by definition of entropies, is smaller of the full entropy. Okay, we know that if you condition on some possible extra knowledge, the entropy can only decrease. Okay, and we have this. And yeah, well, there is a relation between these two randomness in this sense. So the statistical randomness is an upper bound to the private randomness, but we know that in many situations, this bound is far from tight. Okay, so maybe you don't fully understand what is written here, but this first slide is important for what is going to follow. Okay, now for you to understand the difference is and why we are talking about two different properties. Take the following example. So imagine I'm a provider of random number generation, a number generator, and I have technology to do a very good random number generator. For instance, I can prepare photons going into a half-half mirror, and then the photons can take either this path or this path with same probability, and I measure the clicks. So according to quantum physics, this is a perfect quantum random number generator. Okay, so I have a list of bits and that are unpredictable. So quantum physics doesn't tell you which path the photon is going to take, and they are statistically random. So and you come to me, you're the client, and you have two. You want to use this random number generator, okay, for two applications. One is to run numerical simulations, and the other one is for a virtual casino in which you want people to play the roulette. Okay, and so for the first one, you need what I called before statistical randomness. For the other one, you need private randomness. So what I do then is I generate these random numbers in advance before you come with this perfect technology that I have. And the only thing I do, I copy these random numbers into a classical memory. Let's assume that I have some knowledge about the test you're going to implement. So I choose this memory larger than the size of the test you're going to implement. So you won't see any recurrence because the size of the memory is larger than the size of the test you're going to implement. So I copy these bits into the memory, and I'm selling this to you as a random number generator. And the only thing that the machine does is it gives you the bits that were written in the memory and that were produced in advance. So clearly, this machine is, when you run the numerical simulation, these random numbers will be perfect for you, okay, because they are fully random in the sense of stochastically random. Statistically random, sorry. So the sequence of bits has full entropy. So this is very good for your first use case on numerical simulations. But of course, what I can do then when you start playing roulette, you believe that these numbers are random, but I have a perfect copy of these numbers in my place, and then I can get all your money because I can go to your virtual casino and get all your money because I can really predict what is going to happen. Okay, and this is because the randomness, the entropy that condition on what I know is zero. Okay, because I know perfectly what the machine is going to do because I wrote everything inside the machine in advance. Okay, so the fact that we have a machine, which is this classical memory random number generator, and that this device is perfect for one use case and is completely useless for the other use case, means that we are talking about different properties of the system. Okay, so in one case we are talking about stochastic randomness, and the other case we are talking about private randomness. So what is important to understand is when we say random, we have to specify random to whom. So in the first case, you want somehow lack of patterns. So somehow you, when pressing the button here, you don't know which number is going to appear. For you, the numbers look random. And even if you see the k first random bit, you are never going to be able to produce the next one. But for me, the numbers are not random at all because I have a perfect distribution of them. Okay, so I hope this is clear. Now let's see what are the tools we have using classical physics to generate randomness, whatever this means. Okay, so what we have to understand is classical physics is fundamentally deterministic. Okay, so you have So if you have here, I'm not talking about imperfections, but you have a perfect description of your system, the forces, and the initial conditions, okay, then you can predict the future and even the past perfectly. Okay, you have enough computational power. So if we leave aside limitations or imperfections, I can predict the future and the past perfectly given some initial conditions. Okay, so any random process is just a consequence of imperfections or partial knowledge. So there is a typical example, is the roulette. If we play roulette, we cannot predict what is going to happen. But of course, if we have a perfect description of the roulette, the ball, all the relevant physical quantities, we can predict where the ball is going to end. So we can never exclude the existence of an observer that has perfect knowledge about all these elements and can make a perfect prediction. Okay, this perfect ideal observer might sound too much, but also we cannot exclude the existence of an observer who knows better than us about the roulette, because maybe the roulette he can predict better than us the initial position of the ball or the speed, and then the prediction by this observer is better than fully random. And again, this is not science fiction. Maybe you know that in Spain there was a family, Pelayo, and they realized that some roulettes that were used in Spanish casinos, I believe 60s or 70s, they had some patterns, and then it was a large family, so they were playing in many different casinos, and of course that deviation was enough for them to get money. And in fact, at some point, this was the owners of the casino, they found out, and then they couldn't enter the casinos. There is even a book and a movie if you're interested about this, but it proves what I was telling you, okay? So there might be observers who have better knowledge than you, and then things look less random, whatever this means. I think it doesn't mean much. It means that we should not use the word random to describe this thing. Okay, and then still, this is perhaps a process that behaves in a statistically random way, and that can be used for numerical simulations. And this is precisely what the test that we use today is for randomness check. Okay, so they look for patterns to be sure that we have statistical randomness. This is problematic. For instance, if you go to Wikipedia and you write randu, you will find that this is a device that was used in the 60s as a random number generator. So this device was called random at that time. But then one day there was someone had the idea of plotting 3 of these random numbers and plotting them in a x, y, z plane, in a 3-dimensional plane. And suddenly this pattern appear. So clearly the numbers are random. They should equally populate this 1 unit cube, but this was not happening. Clearly these numbers were not random. And then this random number generator that was considered to be random was no longer random after this person had the idea of looking for this pattern. Okay, so this shows that it's not really a very rigorous thing to argue about statistical randomness based on a finite set of tests. Okay, so this is what people usually do, and it is a fact that it has some limitations, but okay, you can increase the battery of statistical tests, and you can somehow get confidence that perhaps there are no relevant patterns in the sequence of bits that you generate. Okay, and again, going back to this memory random number generator that I was telling you about, I mean, this has also exemplifies, it is a device that, as I was telling you, if the size of my memory is larger than any test that you're going to implement, this is a random number generator that will pass any statistical test that you run, okay, for this given size, okay? And this is because these tests do not measure private randomness, they may measure statistical randomness. Okay, remember this device, it's perfect for numerical simulations if the memory is large enough, but it's useless for cryptographic applications. Okay, so then let's try to see how we can generate randomness. And the first thing in physics, and this is also an important message from my talk, we cannot generate randomness from scratch. This is impossible. Okay, so we have to make assumptions about any protocol for randomness generation must be based on assumptions. And by assumptions, I mean modeling. You have to have some understanding of the device to characterize the properties of the output the device produces. Okay, some physical understanding of the physical device. So how do we do this? There exist classical random number generators. Okay, sometimes they are called true random number generators. And for the classical ones, you model things with classical physics, and of course in classical physics, if you model things in a deterministic way, there is no randomness. So you have to introduce by hand some element of stochasticity. Okay, so you may say like, okay, I'm going to use fluctuations in temperature, and okay, you model the fluctuations, how they are. It's a Gaussian with a given width or whatever, and this is what you use to generate the randomness. Okay, and if you don't introduce this element of stochasticity, there is no randomness because, as I was saying, in classical physics, there is no randomness. Okay, so you want to have the modelization of a device for random number generation. So you have to specify how things are produced. So you may say like, okay, I produce this voltage and I apply this application, I apply these operations, and I mix it with another signal that comes from the mouse movements and so on, so on. Okay, you describe all these different pieces of your device. And of course, at some point, you have to say that something here happens with some probability. Otherwise, if everything is deterministic, the outputs will be deterministic. Okay, so by hand, you have to say, you have to introduce some stochasticity here. So you have to introduce by hand some entropy. And perhaps you follow the evolution of this entropy during these processes, and then this tells you the final entropy of the bits. Okay, and of course, if you include larger stochasticity here, you will have more entropy at the output. Okay, so if you have non-stochastic terms, there will be no entropy. The more stochasticity you add, the more entropy you will have at the outputs. Okay, but now if you forget about this, I mean, all what you have is just a convex combination, a mixture of deterministic preparations, okay? And the stochasticity tells you the probability of each of these possible deterministic things that could happen. Okay, so now let's go to private randomness. This is the one that I'm mostly interested in. So here, as I said, you have to describe things not only for the user, but also taking into account the enemy. So you have to think about you have a device and the enemy may have some extra knowledge on the device, like the Pelayos had on the roulette. And a possible way of representing this extra knowledge is through introducing a system that is correlated to your device. Okay, so the enemy can be correlated with your device. And then we will say that some bits produced by your device are random whenever they cannot be predicted by the observer. Okay, by any observer in your physical theory, by any physical observer. Okay, so this is satisfactory because now you see things are not only random to me as a user, but even to any potential enemy. So they are random to everyone. So this is definition. I will elaborate on that. So I think this definition is satisfactory both from a fundamental and applied perspective. So from a fundamental perspective, I think it's difficult to argue that the process is random if someone else can predict it with certainty, okay, or can have some predictability on the process. I wouldn't say that the process is random. It's random to me because I don't have enough knowledge, but it's not random to a person who has this extra knowledge. And from a practical perspective, if you care about cryptography, it's important to be sure that what you generate is private random. Okay, so it's only in your hands, and it cannot be predicted by anyone else. Okay, so the way we quantify this thing, and I mean, this is perhaps blah blah, but we have precise ways of quantifying these things, and usually we do it through through this entropy. So you want to other measures, but basically sort of measures of ignorance of the symbols conditioned on the extra knowledge that the eavesdropper can have. And we want to find, we are paranoid, we want to find these, we want to bound this quantity over the modeling that I use, okay? M represents the modeling of the experiments, so for instance, which states are prepared, which measurements are implemented. So I want to understand under these physical conditions, what is the minimal entropy of my symbols conditioned on the extra knowledge that an eavesdropper can have. I believe these things will become clearer later with some examples. So what is important here to understand is that the amount of randomness depends on what I assume about my devices. And although this sometimes is difficult to solve, it can always be stated. And as such, it's just a matter of, it might be difficult to compute, but it's a quantity that can always be defined and for which we can always try to obtain bounds or characterize it. Okay, so let's stop here just for a while. So here in all what I said so far, I didn't make any reference to quantum physics. Actually, I didn't make references to physical theories, only to classical physics for a while, just to describe how classical random number generators work. But if you forget about this part, I had all the part about definitions of stochastic randomness, private randomness. All these things didn't make any reference to any physical theory. Okay, so there is nothing like classical randomness or quantum randomness. It's just randomness. And we may have ways of generating statistical or private randomness using classical physics or quantum physics. And for that, what is important is the modeling. Okay, so when I specify my device, I will have to describe the physical properties of the device and then try to compute these entropies from the modeling of my device. What you will see is that this is a very simple proof, is that in classical physics, I cannot have a positive number here. Okay, this number, this minimization is always gives 0. Okay, so this number is always equal to 0 in classical physics, precisely because in classical physics there is nothing like any sort of intrinsic randomness. It's everything is a matter of ignorance or lack of knowledge. And if I assume that I'm fighting against an enemy who can have this extra knowledge, then randomness disappears. Again, like the Pelayos, okay, a super Pelayo who is able to predict all the initial conditions of the roulette and then the output of the roulette. Now, the important thing is that in quantum physics, I can design experiments in which the number is positive and I have private randomness. And since I have to leave classical physics, I have to involve non-commuting objects, okay? Because you have commutation, everything is commuting, then I'm back to classical physics, and this will be 0, as you will see. Okay, so all what I say was with no reference to quantum physics. Now let's introduce quantum physics. So we are in a meeting dealing with quantum concepts. So let's try to reason about these things using quantum physics. So the first difference comes because quantum random number generators, meaning quantum devices that produce randomness, they do not require any element of stochasticity. Okay, so to describe the functioning of a quantum random number generator, I don't have to describe like, okay, this happens with some probability, this state is prepared, and with probability this measurement is implemented. I can simply say, as this state is prepared with probability 1, and this measurement is implemented with probability 1. Of course, this will produce randomness, but the description of the device can be done in deterministic terms, and this is impossible for classical random number generators. Okay, so I can say, in the simplest case, I can say that I prepare a spin pointing in the z direction, and I make a spin measurement in the x direction. Okay, so I'm not telling you, I'm not using any stochasticity in the description of my device. I'm just preparing one state with probability 1 and implementing one measurement with probability 1, but I know that this produces perfect randomness. Okay, so all my description of the device is in deterministic terms. At the very end, I can summarize everything as the preparation of a given state and a measurement, and this gives me the random outputs with private randomness. Okay, sometimes in quantum physics, we model things with stochastic terms. So sometimes we know that the preparation might not be pure, might not be ideal, and then we use mixed states. We say that, oh, I don't know if the state, maybe the state psi 1 is prepared with probability p1, the state psi 2 with probability p2, and then you describe this with a mixed state. So you introduce by hand an element of stochasticity, which reflects your possible ignorance on the system. So what is, and this stochastic term, as it happens for classical systems, will increase the amount of stochastic randomness, but as you will see, this does not affect cannot increase and does not increase the amount of private randomness, okay? Because it's important that we are talking about two properties. One property trivially increases by including more stochastic terms, while the other cannot increase, and in fact, often decreases by including stochastic terms in the modeling of the experiment, because we're talking about two different things. Now, if you, maybe a bit more technical slide here. When we model things in quantum random number generators, we have 3 different ways of modeling things. So the first one is something called device-independent approach. In this modeling, I simply say what the device does. So we may say, okay, an entangled state is prepared and some measurements are implemented, but I don't specify which state is prepared and which measurements are implemented. Okay, I don't have time to go through this. It's just a very minimalistic modeling, and you can still produce randomness in this approach. The standard approach is like you say which state is prepared and which measurements are implemented. This is called device dependent. You specify everything that is happening inside the device. and there is some sort of hybrid situation with different levels of description of the device, of the elements of the device. Okay, this is maybe a bit too advanced for the scope of this talk, but I just wanted to say that there are different ways of modeling quantum random number generators. To simplify things, I'm going to focus on the most standard way, which is telling you how the quantum random number generator is what is the composition of the quantum random number generator. Okay, so let me just give some examples to illustrate all what I said. Okay, so I want you to remember that in my opinion, there are two ways, two sides, but actually I would say two properties: stochastic randomness and private randomness. In classical physics, we may be able to generate stochastic randomness. We cannot generate private randomness, and in quantum physics, we can generate private randomness. So let me just give the first example. So imagine that you prepare a spin pointing in the z direction, and you measure the spin along the z direction. So the spin is pointing in the +1 direction. Well, clearly this experiment is going to give you +1, +1, +1 deterministically. Okay, you will see in all what I'm going to say. In the first examples, I won't introduce any stochastic term. Okay, so I will say I prepare this state and I make this measurement. Okay, so clearly here, if I measure sigma z, I will get +1, +1, +1, +1. I don't observe any randomness because I see +1 systematically. And of course, as this is an upper bound to this conditional entropy, this private randomness is also 0, which is trivial. Okay, so now let's put stochasticity. So let's assume that I think that the description of my preparation device is stochastic. Okay, so I know with probability 1 minus p prepares the state up, and with probability p prepares the state down. So when I make the measurement sigma z, okay, then this will be the entropy of this will be the entropy of a symbol for the p and 1 minus p. Okay, because I will see that with the 1 minus p I get +1, and with probability p I get -1. Okay, so the statistical randomness will be the entropy of coin with probability p and 1 minus p. Now, however, if I think of someone who has better knowledge than me, this enemy may actually know which state is being prepared by the source. So at each round, the enemy knows that it's prepared the state +1 and -1. Okay, this varies probability 1 minus p and p, but at each round, he actually knows which state is being prepared. So the enemy can, this is like the Pelagios in this quantum roulette. So the enemy can know which outcome is going to be produced. Okay, and this is why condition on this potential enemy, and I don't want to make assumptions on the enemy. So it's something that does not contradict quantum physics. There might be someone who has a perfect knowledge about what the device is producing. I don't know it, and this is why my description is raw, but there might be someone who knows that. And then this is why the enemy can fully predict the output, and her entropy is then equal to 0. Okay, so this is a situation in which I have stochastic randomness and I don't have private randomness. So if we plot this, and if I now change p, the stochastic randomness increases with the stochasticity of my description. So in the limiting term, this probability is half. So I have the identity here. So it's the maximally stochastic state, the maximally mixed state. And I have a perfect random bit. But against this enemy, at all points, the enemy can make a perfect prediction about my output. So the private randomness is 0, while the stochastic randomness grows with the stochasticity in my modeling. Okay, so now this is what I was explaining to you. Now let's change the measurement. Okay, instead of measuring in the z direction, I measure in the x direction. Still a spin point in the z direction, but I simply change the direction of my measurement. Okay, so this is the stochastic randomness does not change. No, sorry. Now the stochastic randomness changes, and because before I was measuring the z direction, now I'm measuring x. So this is going to be half, 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 half. Okay, so this is equal to 1. But here, the knowledge I have is the same that anyone can have. So my enemy knows that the state is preparing z and measuring x. So the enemy cannot make a good prediction either. According to quantum physics, there is no final description of that. There are no hidden variables, whatever you want to call it. So her entropy is also equal to 1. Okay, so this is a very good situation. Okay, this is like the photons going into the beam splitter. The enemy in advance cannot predict what is going to be obtained. Now, what happens is now I put stochasticity. So now I assume that this prepares states up and down with some probability. Okay, So you can easily see that the stochastic randomness remains equal to 1, okay? Because even if you change between z and minus z, if you measure along the x direction, you get half. Okay, so this doesn't change. And what you can prove, I mean, you have to believe me, but it's rather simple, is that the amount of private randomness now decreases with p. Okay, is equal to this quantity. I don't have time to explain this. It's a very simple calculation. So you can prove that this quantity is now equal to this quantity here, which is strictly smaller than the amount of stochastic randomness that remains equal to 1. Okay, so here you see that the stochastic randomness is 1. Of course, if I put more stochasticity, it remains equal to 1, which is the maximum. But the amount of private randomness that was equal to 1 at the noiseless situation becomes worse and worse when increasing stochasticity, okay? Because again, private randomness cannot increase by adding stochasticity in my modeling, can only remain equal in most of the cases, decreases, and this is what is happening here. Okay, what is the limiting case in the two situations? The limiting case when I take p equal to half, okay? This is what I was showing to you. Okay, in the two situations, I'm simply measuring z or x on the identity, and the two situations give the same result. So the stochastic randomness is equal to 1, and the private randomness is equal to 0. Okay, so this is perfect for numerical simulations, but it's completely useless for cryptography. Because how do we model these things in quantum physics? Well, if you measure identity, it could happen, you cannot exclude, that you're measuring identity, and because the particle you are measuring is fully entangled with another particle that it has. Okay? Okay, this may sound crazy, but you never know. The same way as the casino owners didn't know about the Pelayo. Okay, so from what I see the identity. I cannot exclude that this identity is the result of tracing out one particle of a maximally entangled state, and this extra particle is with its hands. Okay, so this is something perfectly compatible with the description of my experiment. And I know that if I measure sigma z, the enemy can measure sigma z, and she will get a perfect copy of my output. And if I measure sigma x, the enemy can measure sigma x, and she will get a perfect copy of my output. Okay, so in principle, according to the theory, I cannot exclude the possibility that an eavesdropper that is perfectly correlated with my system and that can make a measurement on her particle and get a perfect prediction of my measurement output. And this is why I have 0 private randomness while having perfect randomness. I think if you understand this example, I think everything is clear about what I said before. And this also tells you why, if you know about classical physics and how we get classical physics from quantum physics, this is why you cannot get randomness from classical devices. Okay, so the way we get classical physics from quantum physics is we work with a basis. We don't work with coincidences. Everything happens in a given basis, say the computational basis. States can be pure, also mixed, and I always measure in the same basis. Okay, so you see everything commutes, everything is in the same basis. If I have a stochastic state, I will write it as a mixed state in quantum physics, but again, it's a probability distribution. And then if I see the output, I will make this measurement, and I will see some entropy here. But if I want to measure this quantity, which is the amount of private randomness, well, I can never exclude that this looks mixed because entangled with another particle. This is the global state. If you want, it has a perfect copy of my state. Okay, perfectly correlated copy through this instruction here. And by making the same measurement, he gets a perfect copy, she gets a perfect copy of my output. Okay, and this explains why the private randomness is 0 in classical physics, while the stochastic randomness can be non-zero, and in fact is the entropy of this distribution here. Okay, so again, classical physics can give you systems that are good for numerical simulations because they generate observed entropy, stochastic entropy, but they cannot give you any guarantee about the private randomness. Okay, so if this is clear, now I will end up with some short description about things we did in the group, because this is something that we like, because I think it's fundamental for our understanding of nature, but also because we also use this randomness for quantum communication. Actually, some quantum computers, ion trap quantum computers, have been used to simulate certified randomness. So it's also a possible application of quantum computers. But again, in my case, I'm more interested in randomness for quantum cryptography. And this is a paper we published last year on the randomness of a quantum state. Okay, so the question is similar to what I was telling you. Okay, so you have a state. Here I was having the state up. In one case, I can generate private randomness. Depending on the measurement, I can generate private randomness or zero randomness. Okay, so there are some measurements that generate zero randomness, and some other measurements generate perfect randomness for the same state. So our goal was to, if you give me a state, try to understand what is the optimal measurement to implement and how much randomness this optimal measurement generates. So if you want to phrase it in a different way, is we want to understand how much randomness a quantum state contains, how much randomness you can extract from it by making the right measurement, the optimal measurement. So that was our motivation. So this is why the paper is called Maximal Intrinsic or Private Randomness of a Quantum State. Okay, I give you a state, I give you the promise. Okay, this is that you have. Tell me what is the optimal recipe to extract the randomness of the quantum state. So the logic is the following. This is the state you give me. I have a description. I have to choose a basis. With this basis, I will have some outputs. The state might be mixed, and I will always assume, because I'm paranoid, that if the state is mixed, it will be because it's correlated with someone. Now, if you only look at stochastic randomness, okay, we know that there's always a measurement that gives you perfect entropic bits for any state, okay? Because what you can always do is you can take the eigenstates of your state and take a basis that is called mutually unbiased with respect to the eigenbasis. So if you give me a state I can always find a basis whose overlap is equal to 1D for all the elements of the different bases. Okay, so for instance, if you take, in the case of qubits, if you take Z and X or Y, these bases are mutually unbiased, which because I take elements of Z, they give, they have overlap half with elements of the X basis or the Y basis. Okay, so the optimization of stochastic randomness for any quantum state is trivial. You only have to take a basis that is mutually unbiased with the eigenbasis of the state, and this gives you perfect stochastic randomness log 2D of stochastic randomness. So this problem is trivial. So what is non-trivial is the problem of how to generate private randomness and how much private randomness you can generate. So we model things in the same way. So if I see mixedness, it's because my state might be correlated with the eavesdropper. So I will write this in this way. And then what I will do, I will make a measurement here, and then my measurement will project each state into something depending on the output. And I want to understand the entropic properties of this output depending on the measurement I implement. So this is a way of measuring randomness, computing the conditional entropy that now will be a function of the measurement I implement, and I want to maximize this entropy for the eavesdropper. Okay, so I have to solve this optimization problem. Or we also use another definition of randomness, which is related to what things I was saying before. I can also see which guesses it can produce for my outputs by making a measurement of her system. Okay, and I then compute her guessing probability. So what is the probability that her outputs are equal to my outputs? And okay, there is a quantity that measures that, and I want to minimize her guessing probability. Okay, this is also a measure of randomness. So we stated two optimization problems, one in terms of entropy, the other one in terms of guessing probability. And our idea was, okay, how to solve these optimization problems, find the optimal measurements that give me how much randomness I have here measured by the guessing probability of. And we solved this problem. Okay, so just for you to have an idea of what we did was, okay, you have a qubit, and any qubit can be written in this form, okay, not zero with a given direction. So any qubit is just an arrow in the block sphere. I can always choose the computational basis as the eigenstate, and then I can always write it in this way. And well, you can easily conjecture that the optimal measurement also for private randomness is a mutually unbiased basis. It is the optimal for stochastic randomness, but it happens to be also the optimal for private randomness. And then you can see that the best that the eavesdropper can do, she can prepare this state and this state with probability half. So on average, it looks like the state I'm seeing. And whenever she prepares this state, she will guess this output. And if she prepares this state, she will guess this output. And this gives her guessing probability. Okay, this is an example for qubits. We solved this problem in full generality, and we computed the amount of randomness for any state. If you compute by entropy, this is the quantity you get. And if you compute by the guessing probability, this is the quantity you get. Okay, some limits here. If the state is pure, the entropy is 0, so the amount of private randomness is log 2 over d, as it should be. Okay. If the state is pure, this trace is equal to 1, and the guessing probability is 1 over d, as it should be. So the enemy has no clue. It can be any of the d possible results with same probability. If the state is fully mixed, so this quantity is log d, so private randomness is 0, and this quantity is equal to square root of d. To the square makes d, divided by d makes 1. Okay, so when the state is the identity, there is no private randomness. And for all the cases in between, so here randomness is 1, here randomness is 0, and in between, the amount of randomness is measured by these two quantities. Okay, so I will finish with the conclusions of this talk that in which I told you about randomness. So the first take-home messages I would like you to understand is that statistical private randomness are two different properties. I can design a machine that is perfect for statistical randomness and completely useless for private randomness. Statistical randomness is measured by the entropy of the outputs. Private randomness is measured by the conditional entropy. Statistical randomness is good for simulation, useless for cryptography, and we need private randomness for cryptography. And the standards we have, they focus only on statistical randomness. We don't have any standard for private randomness because there is nothing like private randomness in classical physics. Now, second batch of conclusions, now more related to physics. When we want to talk about physical devices for random number generation, we need to model these devices. Okay, this is essential, and the amount of randomness we see depends on the modeling of these devices. It's not that there is classical or quantum randomness. We have classical or quantum devices to generate randomness, and we model according to classical or quantum physics. In classical physics, I can have statistical randomness, but I need to add some stochastic terms by hand. And private randomness certification is impossible. Okay, this is a very simple proof that I show to you based on the fact that things commute and everything can be expressed on a given basis. In quantum physics, private randomness is possible, and I don't need to add any stochastic term by hand. I can simply say I prepare this state and I implement this measurement. So this also solves the conflict I was telling you about. So this is what I was telling you at the very beginning of my talk. So physicists say that there is a force form of randomness. If you talk to some people, they will tell you there is no need for a new standard for a randomness characterization. Well, we are not talking about quantum randomness. We are actually talking about private randomness. Okay, and in the first claim, what we meant is actually that we can have quantum devices that produce certified private randomness, which is impossible in classical physics. And the existing standard refers to stochastic randomness, and this is why it's not in contradiction with this first statement. But of course, if the existing standard is for stochastic randomness, but we have private randomness, this means that we need a standard for private randomness in which quantum random number generators will really give an advantage. Okay, this is all what I wanted to tell you. Thanks for your attention.